Hello everyone, welcome to the lecture 2 System Structure and Processes. So in this lecture you are going to see the structure of different operating systems. So any operating system is designed using modular approach. Modular approach means operating systems programs are divided into different layers. So such kind of architecture is called modular design architecture. So for example, if you take the MS-DOS operating system, very old operating system, the architecture is like this. We have the hardware at the bottom, above which we have the kernel. The kernel interface with the hardware using device drivers, and the kernel also has various other functions such as memory management, process management, disk scheduling. Then it has a scheduler, dispatcher. So these are the core functionality of a kernel. Kernel is a very important component of an operating system. It can be called as a heart of an operating system. Above the kernel we have system programs and application programs, and this system and application programs, of course, they interact with the kernel using system call. It's an interface through which the application and system programs interact with the kernel. So this is a structure of a simple disk operating system, and this is the architecture of Unix operating system. In the Unix operating system also same like this. We have kernel here. So the kernel, as I told, is a very important component of any operating system. It has various functionalities. The very important functionalities which I want to discuss now is CPU scheduling. So like when many processes they want to use the CPU, the process will be allocated to the CPU according to these scheduling algorithms, FCFS, round robin, priority based scheduling. So these scheduling algorithms are in the code for these algorithms are inside the kernel, and memory management functionality also is supported in the kernel. Virtual memory you will see in chapter 9. Swap space, sending the process from the main memory to the swap space and swapping out. When you have less amount of memory space, you have more number of processes, then some process would be swapped out, sent out to the swap space. So, and whenever the space is created, the process which is in the swap space would be brought back, swap in. So this concept is called virtual memory. It is also part of the kernel. And file system also is interface through which the files are stored, retrieved, managed. So that system also is part of the kernel. And device drivers like disk driver also part of the kernel. Terminal means output devices like monitor. So these device drivers also part of the kernel. So these are the very important programs or modules inside the kernel, functionally supported by the kernel. And you have the system call application, system call interface, And this system call interface is a library through which the application and system programs interact with the kernel. So above the kernel you have shell. Shell is an interface through which the user interacts with the kernel. If the user wants to create a folder, so the user has to use the shell command to create a folder. If the user wants to create a file, if the user wants to remove the folder, remove the file, if the user wants to set file permission, read permission, write permission, executable permission to a specific user or to a specific group, then the shell commands are necessary. If the user wants to open a file, edit a file, the shell commands are necessary. So the shell is a interface through which the user interacts with the kernel. And once again, this shell is a system program, and this system program, once again, to interact with the kernel, it uses the system call interface. System call means it's an interface through which the application and the system programs interact with the kernel. So this is a structure of a Unix operating system. So basically the structure of the different operating systems are classified into monolithic. You can see here, this is a comparison of different operating systems. So different operating systems structures are classified into monolithic, microkernel, hybrid. This is a very general category. So monolithic means this is a good example. So monolithic means the kernel would be very big. So most of the operating system functionalities would be inside the kernel. So you can see here CPU scheduling, memory management, virtual memory management, file system, and device drivers. So all these functionalities are inside the kernel. Now just compare this architecture with another architecture. It's called microkernel architecture. In the microkernel architecture, the kernel would be very light. It won't be heavy. It won't have all the functionalities. So here in the microkernel architecture, for example, it has a CPU scheduling functionality, and here also the CPU scheduling functionality is in the kernel part. This is example for monolithic, this one. Whereas in the microkernel, the CPU scheduling is supported by the kernel, memory management also supported by the kernel. And whereas if you see the file system, it is moved away from the kernel to the upper layer, and also device driver also moved up. It is moved away from the kernel to the upper layer. Whereas in the monolithic architecture, file system is inside the kernel and device drivers also inside the kernel. So this is a simple comparison. Okay, so here this is the monolithic architecture where you have too many functionalities inside the kernel. The kernel is very heavy. Whereas in the microkernel architecture, the kernel is micro, that is lighter. It is in the lighter form. It's not heavy. It doesn't have too many functionalities. Some of the functionalities in the kernel, which is supported by the kernel in the monolithic architecture, is moved away from the kernel to the upper layer. Example, file system and device driver. Once again, this different modules interact with each other using inter-process communication, using message passing system. So they send and receive messages. They communicate with each other. So in the microkernel architecture, different modules, they interact with each other. They communicate with each other using inter-process communication. So in the microkernel system architecture, different components of the operating system interact with each other through the inter-process communication. Example, message passing system. They send and receive messages. So this is a microkernel architecture. If you see some of the operating systems, example Linux, they are monolithic in nature. That means most of the components are inside the kernel, and the kernel is very heavier. And some of the operating systems given here are microkernel, example MK Linux, Minix, then and GNU Mac. So these are examples for microkernel. So microkernel means some of the components are moved away from the kernel into the upper layer. So this one is a very useful stuff actually. Wikipedia.org wiki comparison of operating system kernels. You can go through that. So another class of operating system architecture is also there. It is called hybrid. Hybrid means it's a balanced approach between the monolithic and microkernel. It's between the monolithic and microkernel. And the Windows operating system basically is of hybrid nature. So Windows 2007, 8, Windows Phone 8.1, Windows 10, it's of hybrid architecture nature. Solaris, it's a Unix operating system. It is monolithic. Already we have discussed that Unix is here. So actually Unix means there are different flavors of Unix. One such flavor is called Solaris Linux. So far what you have understood is that any operating system architecture can be classified into either monolithic, example Unix, or just a minute. So to continue with that, microkernel system architecture example Mac OS 264. Okay, and in the microkernel architecture basically some of the components from the kernel space is moved to the upper layer, okay, user space that's up above the kernel. They are not in the kernel architecture. So example Mac OS X kernel, but you can find many examples from this link. Microkernel, so here Mini X kernel, MK Linux, so many examples. So many operating systems are based on microkernel architecture. So communication takes place between the different components of this architecture using the message passing system. So actually you can see here the file system and the device drivers, they communicate with each other using inter-process communication, message passing system. They send and receive messages. So what is a message passing system? Once again we would discuss in detail in the later topics, inter-process communication topic. So the process basically they communicate with each other by sharing the memory. That is one option. Another option is by sending and receiving messages. So here in the microkernel architecture, so these different modules like file system and device driver example, they communicate with each other using message passing system. What are the benefits of microkernel architecture? It is very easier to extend a microkernel. The thing is that if you want to add a new functionality, then it can be easily brought in inside the microkernel architecture very easily, because you see the kernel is very light. You can have the component above the kernel architecture, and you can add a new component, and you can make that component communicate with the other components through the message passing system. And also this type of architecture is very light, not heavy. The kernel is so light that you can make this compatible with the new types of hardware architectures, with any new system architecture. And also it's more reliable, because you see the kernel component, kernel is not heavy with many programs. So most of the programs are shifted to the above top layer, above the kernel layer. So less code means less trouble. So it improves the reliability, and also the secure, it is more secure than the monolithic architecture. However, there is one drawback in this system, is that you have to make these components communicate with each other using the message passing system, and this message passing system has to go via the kernel, through the kernel. So this is one overhead. It would affect the performance overhead of user space to kernel space communication. So when any system program, the programs in the kernel mode is running, when any program inside the kernel, if it is running in the kernel mode. And when any program which is not part of the kernel, which is above the kernel mode, which is from the upper layer, user layer, it is running in user mode. So when these components, they have to communicate with each other, and also when they want to interact with the kernel, then user mode to a system has to, when a system is running, it has to run in either user mode or kernel mode. So the system has to switch between the user mode and the kernel mode frequently. It would affect the performance. So we have discussed these things. Now I am moving on to the Android phone. Android, Android, your mobile phone, it's operating system in your in most of our mobile phones, Android. The another one is iOS. So here in the Android operating system, in the kernel of the Android operating system supports process management, memory management, device driver management. So device driver management, memory management, and process management, they are inside the kernel in the Android operating system. And also there is one more functionality supported in the Android, is called power management, that is also in the kernel. And the Android phone basically has a virtual machine running that is called Dalvik virtual machine, and it has some library files, and also the applications which can be deployed in the Android operating system can be developed using Java plus API, application programming interface. So using these APIs, you can develop many applications that can be deployed in the Android operating system. And once again, it would run inside a virtual machine which is running in the Android, that's called Dalvik virtual machine. So these are the important points about the Android architecture. So this is what we are discussing in the slide number 13, hierarchical structure in OS. So OS means different operating system has different structure. Some architectures are monolithic, some are microkernel, some are hybrid. This is called when you divide the components of a program into different layers. It's called modular approach, modularity. You can see modularity. So different operating system has different level of degree of modularity. So for example, if you see the microkernel, the modularity is more in the case of monolithic, everything is stuffed into the same layer. Okay, so different operating system has different modularity. So whatever the case, let's go back to this this architecture. This is the kernel. Above the kernel you have the user level. In the user level you have shell programs, then you have application programs, utility programs. All these programs interact with the kernel using an interface called system call. So whether it's a system shell, for example, you want to create a folder, you go to a shell prompt and you create a folder like this, cmd my folder. I create a folder. So whether we create a folder or anything, it is achieved. This shell programs that interact with the kernel using the system call. And even if the application programs like Word, Excel, PowerPoint, or whatever programs we develop, they interact with the kernel using the system call. Okay, it's an interface through which the system and application programs interact with the kernel. So that's the point here. What's a system call? Interface to the between the application and system programs and the kernel. So the application and system programs interact with the kernel using the system call. It is developed using languages like C and C++, same like kernel. Whatever the languages of the kernel, using that these system calls are developed. Example, C and C++. If the kernel is developed using C and C++, then the system calls also developed using C and C++. And the group of system calls, there are a bunch of system calls in any system, and they are together called as a programmer interface to the system. For Windows, the example for system call is Win32 API. For Unix, POSIX API. For Java API. So these are the examples for system calls. So any system program or application program, if they want to access any hardware resource, they cannot do directly. They have to go through the kernel. So to communicate to the kernel, they have to use a system call. Example, if just now I said that from the shell I want to create a folder, or I want to open a file, I want to delete a file, I want to edit a file. So whatever the case may be, you have a specific unique system call for that particular purpose. You have many system calls for different purposes. So examples for system calls are as follows. The system calls can be classified into process control, file manipulation, device manipulation, housekeeping, communication. Already we have discussed what is a process management. Process means program which is under execution, which is running. So if you want to create a process, you need a system call. If you want to, if the process has to terminate, exit, then it needs a system call. If it wants to temporarily get suspended, we have discussed this scenario before, and once again the process has to resume back to running state, then a system call is necessary. If the process has to be terminated abnormally, that is see, I go like this, and I want to end the task, abort, then you need a system call. So to create a file, to write some data in the file, open a file or close a file, also you need system calls. Then device management. So when any process has to access a device, input or output device or whatever device it might be, basically the process has to send a request, and this request goes to the operating system, and the operating system is the one who decides whether this particular resource has to be allocated to that particular process. So the process, if it wants any resource, it has to call the request system call, and once the process finishes the task with that particular resource, then it can release the resource using release the device using the release system call. And if it wants to read some data on a particular device, it can use read and write system calls. Then to set the time of your system, or to get the time or date of your system, you need some system calls. That kind of system calls are classified into housekeeping type. Then setting or getting the attributes to a file or process device belongs to housekeeping purpose, that we will discuss in the later topics, like read permission, write permission, executable permission to a file. Okay, so that kind of things comes under the housekeeping type of system call. Communication. So if when the processors wants to communicate with each other, then you need communication type system calls, and the processors they basically use the system calls like create a link, set up the link, send the message, receive the message. Okay, for example, when we processors, they communicate using a socket, and they use the send and receive message APIs. So once again, let me explain this back. The system calls are classified into many types: process control, file manipulation, device manipulation, housekeeping, and communication. So here in this slide you can see examples for different system calls for different categories under Windows and Unix operating system. So if for the process control type system calls, you can see for Windows operating system these three system calls are given, and these are the system calls for the Unix. Example, let me put you a question. Dash is a system call which can in Unix operating system to create a process. Fork system call. So, and also this wait is a system call when any process wants to wait. It wants to wait for another process. For example, the parent process wants to wait for the child. So you can ask, what is a parent child? So you will see in the next chapter. And also about the fork system call, we would I would explain in the next topic, third chapter. So in this slide you can see how a system call is implemented. So this is a user application, or it might be a shell system program. For example, here okay, so what's happening is that from the user is opening a file. Okay, so you have some file on your desktop. You just double click and you try to open your file. Let's say it's a text file. Okay, so what happens is that the user is trying to open your file through some application. What happens is that the application calls a system call, and that it uses the API, application programming interface, open, and that is mapped to a system call in the system call library, and that system call is in the kernel. So that particular system call is invoked, and that system call basically opens the file, and once the file is opened, the control is returned back to the user application. Let me repeat once again. So the user is trying to open a file through some application, example notepad. So that application uses a API, let's say open, and that API is mapped to a system call in the system call library, and that system call, okay, is invoked in the kernel. Each and every system call has a number, so that particular system call is invoked, and that system call opens the file from the storage, and now the control is returned back to the user application. So this diagram shows the relationship between the application programming interface, system call, and the kernel. So API means basically our notepad or Java program or C, C++, Python program. They use some functions, methods we call, okay, to open a file or to close a file or to read from a file or write some data in the file. So that's called API, application programming interface. So once that application uses that API, it is mapped, connected to a system call in the system call library. It is the interface between the system and application program and the kernel. So this API is mapped to the system call, and the system call is invoked, called, and the system call runs. Now the system call, what is the functionality of that particular system call? It is this particular system call has to open the file. Once the file is open, then the control return back to the application program. This is what explained in this slide number 19. So let's come back to the concept. What's a process? Process is nothing but a program which is running or which is under execution. And also when a process is created, some informations about that process are stored in the system. So a data structure called process control block, PCB, is created, and this PCB stores the information about each and every process. So for each and every process there is a separate PCB that stores the information about the process. So dash stores the information about a process. Process control block, PCB, stores the information about the process. So for different process, is there different PCB? Yeah, for each and every process there are separate PCBs. So now once again, the operating system, when a process is created, it stores some information about a process, right? Okay, now the question is, what kind of information does the process operating system stores about a process? It stores the information such as code section, data section, process tag, program counter, contents of your CPU register, memory management, and accounting information. Let me explain with a simple example. So now we are discussing about these different components of a process. So when a process is created, information about a process is stored in the process control block. These are the different types of informations which are stored about a process. So the first part is any process is nothing but some program which is running, right? So that program is made up of some source code. Example, now when I run, it becomes a process. So now this process has this source code. Now you see this program I'm running, it's a program, it's when I'm running, so it's continuously running now. So it's a process actually. This process is running. Why it's continuously running? Because I put some while loop here. So any program would have a code section. So when the process is running, the code for that process has to be, for that program has to be stored. The information about the code, source code, has to be stored. So that information would be covered, stored in the code section. And data section means the information about the global variables. So these are the global variables A and B. They are visible inside the class. Whereas the C here, it's not a global variable, it's a local variable. It is defined within this main method. It is not visible outside this main method. So for any process, there might be some global variables. So information about the global variables in any program is stored under data section. And the third one part is called process stack. So in this program, you can see this C is a local variable. So the information about the local variables in any program is stored under process stack section. And also it stores information about methods, sub-methods. Okay. For example, if it has one more method, that is void add, then these information about the methods and local variables are stored in the process stack. Program counter, it contains the information about the instruction to be executed next. So it has a pointer to some place in the program. So if you see this program, okay, you have instruction 1, instruction 2, like that instruction. Okay, where many instructions are there inside this source code. So now which instruction has to be executed next, that information is stored in the program counter part of process information. And also for each and every process, when the process is running, it stores some information in the CPU registers temporarily. You will see in chapter 5, process synchronization. So if process is updating some data, a particular process is updating some data, okay, then when that particular data is updated, then it needs registers to store the data in temporary manner. So when that process is getting executed and when that process is updating the data, these data values are stored in the CPU registers. So when the process is running, when that update is not completed, I have told in the before, the process sometimes before it completes a task, it has to be preempted. It has to be taken out from the CPU. It's called context switching. The CPU has to switch from one process to another, because we have this, you will see in chapter 4 in detail. In round robin scheduling algorithm example, when a process time quantum expires, for each and every process there is a time quantum. When the time quantum expires, it has to the process has to be suspended from the CPU, and it has to go back to the queue, and its turn will come back again. So this register store basically whatever the data that were held in the CPU register when the process was running, that values has to be stored in this particular part of the process information. So whenever a process is running, please try to keep things simple. Whenever a process is running, it needs register to store some values temporarily. Okay, so for each and every process, okay, CPU register values are very important. It stores the information about the values in the register. And also a process, for each and every process there is a memory management information, that is what is the address space of this process in the memory, in which part of the memory this particular process is stored. When we discuss the later topics, memory management is implemented using a technique called paging, segmentation, etc. Okay, so there you will understand very clearly. So take a particular process, that particular process would be split into many components called pages, and these pages would be stored in memory, main memory. Okay, so for each and every process the operating system should store the information, that is for this particular process is stored in which part of the memory. So for each and every process the operating system stores the memory management information, and also for each and every process who started the process, who owns the process, how long this process is running, how much CPU time it is consuming. You can see here task manager. Okay, so a particular process, how much CPU time, how much memory it is consuming, how much read and write operation it is doing with the disk, how much data it is transmitting over the network. All these sort of informations are stored about the all these sort of informations are stored by the operating system about each and every process, and these informations are stored in a structure called process control block. Each and every process has separate process control block. For example, each and every student in the college has a file, okay, student ID number, and information about each and every student is stored in a separate file. Similarly, information about each and every process is stored in process control block. Each and every process has a ID number, unique ID number. So these are the different informations about each and every process. Okay, so next one is, what is a process state? So the process, when it is running, it would enter different state. When a process is created, then it goes to a state called new, and when it is running with the CPU, it is in the running state. Okay, you are running a process. First it will go to the new state. From new it goes to the new it will go to the ready state. So let me explain with you. Okay, there will be some diagram here. So you can see now, let's say so when your program is started, it would enter the job queue, let's say J1, J2, J3, J4, and from the J queue the job would be transferred into a ready queue in the main memory, and here it is called as a process P1, P2, P3. Okay, example, assume. So let's say we are starting 4 jobs, we are 4 programs you are invoking. So it is coming to the job queue first, J1, J2, J3, J4 as J1, J2, J3, J4. Then there is a program called long-term scheduler. It would select the jobs in the job queue and transfer that jobs to the ready queue. It's a queue which would store the process. Now it is called a process P1. This is converted into a process. It's running. Okay, it's ready to run. So when a process is created and when it enters the ready queue, it is in ready state. When a process is created, it is in new state. Okay, now it is entering the new state here, and from once it enters the new state, it is coming to the ready queue, and in the ready queue the process is in ready state. So when a process is created, it is new. Then after that the process is transferred to the ready queue. Okay, so let's say there are 3 processes in the ready queue. In the ready queue, basically they are waiting for the CPU. So now this among the 3 processes P1 and P2, 3, which one would get the CPU? That would be decided by the scheduling algorithm, round robin scheduling algorithm, priority based scheduling algorithm, FCFS scheduling algorithm, chapter 4. Example, FCFS means the process which come first to the ready queue will get the CPU first. Example, let us assume among the 3 P1 and P2 and P3, let us assume P3 came first. So according to the FCFS algorithm, P3 will get the CPU first. Clear? Suppose the algorithm is SJF, shortest job first. Then what happens? This algorithm will compare P1, P2, P3 size. Which among the 3 is small, so that process would get the CPU first, the smallest first. So there are different algorithms. According to the algorithms, the process would be given to the CPU. Understand? The CPU would be allocated to the process. That is a correct way to explain. So next, when now the P1, P2, P3 are in the ready queue, let us assume some algorithm is picking up the P3 first. So P3 is selected first from the ready queue. So P3, let us say, is removed here, and P3 is running with the CPU now. It's running now. So P3 is using the CPU. So when the process is running with the CPU, it is in the running state. Now let's go back to this program. When a program is running, now this program, for example, if you see, it is continuously running, and when it is running, please understand, it is continuously printing the C. It is output statement. It is a output statement. It is printing. So when any process is doing input or output, when it is reading some data from the mouse, or when it is reading some data from the keyboard, or when it is reading some data from the disk, or when it is writing some data on the disk, or when it is sending some data to the output devices, monitor, then that particular point of time the CPU becomes idle. The process is not executed by the CPU at that particular point of time. Why? Because that process is doing input output operation. Example, let us say this Java program, when it is printing C, that time CPU is not executing this process. Why? Because it is printing, doing the output operation. So when a process is doing output operation, it is not consuming the CPU cycle. So CPU becomes idle. So what happens now? Example, if the P3 is doing some input or output operation, then the P3 is removed from the CPU. It goes to IO queue here. It goes to this IO queue. When it goes to the IO queue, it is in waiting state. So the process is waiting for some event to occur, input or output operation. So the basic thing to be understood here is whenever any process or thread is doing input or output operation, then the process goes from the CPU to the IO queue or device queue, input output device queue. So when the process enters this queue, it is in waiting state. Clear? Now let's say when this P3 goes to the waiting state here, then P1 and P2 are waiting for the CPU. So algorithm will select any one, P1 or P2, according to the criteria of different algorithms. Suppose P2 is selected, so P2 is running now. Okay, and where is the P3? P3 is here in this queue. Why it is here? Because it is doing some input or output operation. When the P3 finishes the input or output operation, it will go back to the queue and it will stand in the queue. It will go back to the ready queue. When the P3 example finishes the input or output operation, it will go back to the ready queue. Now meantime, the P2 is running with the CPU. Once the P2 basically what is that, suppose I remove the while loop. Now what happens? I run the program, it is printing the output, doing the calculation, printing the output. Program is stopped now, terminated. Okay, when I am running, it is now printing the result and it is terminated. Clear? So what is this? When a program finishes all the talimat, all the instructions, what happens is that the process is terminated. When all the instruction is finished, then the process enters the terminated state. So these are the different states of a process. New, when the process is created for the first time, the initial state is new state. So once the process is created, it enters the new state, and then from the job queue, the process, it will go to the ready queue, okay, in the main memory. And when it comes to the ready queue in the main memory, it is in the ready state. Then from the main ready queue, a process would be selected by the scheduling algorithm, and the operating system would allocate the CPU to that particular process. Example, okay, here P2. Okay, so okay, now the P2 is running, is using the CPU, it is running with the CPU, so it is in running state. Now suppose if the P2 wants to do some input or output operation, okay, input or output operation, then it will go to the input output queue. If it is not doing any input or output operation, then it will not go to the IO queue. Remember this. Okay, so after finishing the input output, it will come back to the ready queue, and then again it will get the CPU. If the process finishes all the instruction, then it will go to the exit state or terminated state. So these are the different process states. Okay, you can ask, what about these things? You will understand this in the later topics, because now it's not the time to explain these stuffs. Clear? So now, as of now, just try to understand what are the different states of a process: new, ready, running, waiting, and terminated. Now let me put some questions to you. Okay, when a job goes from the job queue to the ready queue, in the ready queue, the process is in which state? The answer is, it is in ready state. Now when the process goes from the ready queue, goes out from the ready queue, and when it is running with the CPU, it is in which state? It is in running state. When a process, running process, encounters any input or output talimat, input or output instruction, it would go to which queue? IO queue or device queue, or another name is waiting queue. Okay, when a process goes to this queue, IO queue or waiting queue or device queue, it is in which state? It is in waiting state. When a process finishes all the instruction, then it would go to terminated state. Okay, so this diagram shows how a process state changes from how a process changes its state from changes from one state to another. So this you need little more time to get to be understood. Just wait for some more time. What are the different types of queues in a system? The system basically has some queues. The important queues are this: job queue. So when a process is created, okay, what happens? It enters the job queue. So all the process in the systems are stored in the job queue. Next one is ready queue. So this is a queue which stores the processes which are waiting for the CPU, okay, residing in the main memory and waiting for the CPU. And next one is called device queue. So you can see this diagram. Device queue or IO queue, say whenever any process, if it is doing input or output operation, or when it is waiting for a particular device, then it would be stored in device queue or IO queue. Okay, so what are the different types of queues? Job queue. Whenever a program is invoked, started, it enters the job queue first. So you can say the job queue stores all the processes or jobs in a system, and from the job queue the process will come to the ready queue. The ready queue would be in the main memory, understand? And the ready queue has the processes which are waiting for the CPU, which are waiting to get executed by the CPU. And device queue is a queue in which a process would be stored when it is doing input or output operation. So these are the different types of queues. Now there are two important programs inside the operating system kernel. Long-term scheduler and short-term scheduler. Just now we discussed about two queues, job queue and ready queue. Job queue and ready queue. So the long-term scheduler is a program. Long-term scheduler is a program which transfers the, you can see here, transfers the jobs from the job queue to the ready queue. So when it is transferred to the ready queue, it becomes process, and okay, in the ready queue it becomes a process and it waits for the CPU. So long-term scheduler is a program in the kernel of the operating system. This program, where it is in the kernel. And what is the functionality of this program? It decides, it schedules which jobs in the job queue has to be transferred to the ready queue. Okay, next one is short-term scheduler. Short-term scheduler means it is a program made up of different algorithms. Okay, so short-term scheduler decides which process in the ready queue has to be allocated the CPU. So CPU has to be allocated to which process in the ready queue. That is decided by the short-term scheduler. Suppose you have three processes. So which process should be given the CPU? That is decided by the short-term scheduler. Now you have 4 jobs. Which job has to be transferred to the ready queue? That would be decided by the long-term scheduler. So this is a very important diagram which shows how a process is transferred from one queue to another, and this diagram is called queuing diagram, and it represents queues, different queues. Here you can assume job queue and different resources, and how the control flows, how the process moves from one queue to another. So remaining topics, I prefer some practical explanation also. So I shall continue this topic in the next class with practical explanation. So before that, I want you to finish the lab 1, installation of some Linux operating system inside the virtual machine. So once you install that, we can create a simple C program which uses some system calls like fork to create a child process. So once that program is developed by you, you can understand very clearly about these concepts. So thank you very much. With this I conclude today's topic.